Hello everyone, my name is Matvey Kachkov, and today me and my colleague Vladislav Ivchuk will present you with the topic multi-threading and multiprocessing in Python. Let's start with a little bit of theory. The CPU, Central Processing Unit or processor, manages the fundamental computational work of the computer. CPUs have one or more cores, allowing the processor to execute code simultaneously. Computers originally had only one core, but today modern computers have from 2 to 128 cores, meaning that taking advantage of more than one can dramatically improve processing time. GPU stands for Graphics Processor Unit and is the part of the PC which is responsible for the on-screen images you can see. Their highly parallel structure makes them more efficient than CPUs for algorithms that process large blocks of data in parallel. We should also distinguish between physical and logical core. Physical cores are a number of actual hardware components. Logical cores are the number of physical cores times the number of threads that can run on each core through the use of multi-threading. So the real question is, does Python take advantage of multiple cores? And the answer is not really, since the Python interpreter was designed to run the instructions serially. But have no fear, this limitation can be bypassed by the use of parallel processing, namely multi-threading and multiprocessing. Before explaining the essence of the parallel processing, let me also clarify the difference between CPU and input-output bound programs. CPU-bound program is a program that would go faster if CPU were faster. In other words, it spends the majority of its time simply using the CPU doing calculations. A program that computes new digits of pi number will typically be the CPU-bound, so it just crunching numbers. A program is input-bound if it would go faster when the input-output subsystem were faster. So the examples of such processes are the call to a web service, interaction with the database, and interaction with the file system, and of course interaction with the user, with a real human being. I will explain you why do we actually need parallelization, multiprocessing and multi-threading. Python is a great programming language, and it's like a Swiss knife that's used in multiple areas. For example, analyzing and visualizing data, training machine learning models, building APIs, and much more things. But the versatility of this language, among other things, comes with a price. Python is slow compared to other programming languages. And moreover, every data science project faces an inevitable challenge: speed. So when working with larger data sets leads to slower processing, you will eventually have to think about optimizing your algorithm's runtime. What is actually parallel processing? Basically, doing two things at the same time, either running code simultaneously on different cores or running code on the same core and achieving speedups by taking advantage of so-called wasted CPU cycles, while your program is waiting for external resources, for example, file loading or API calls. As an example, here on the left you can see a normal program which downloads a list of URLs one at a time using a single thread. And here on the right side you can see the same program using two threads. It divides URLs among threads, giving us nearly a 2 times speed boost. Fundamentally, multiprocessing and threading are two ways to achieve parallel computing, using processes and threads respectively as the processing agents. And to understand how this works, we have to clarify what processes and threads are. So, a process is an instance of a computer program being executed. Each process has its own memory space and it uses which it uses to store the instructions being run, as well as any data it needs to store and access to execute. Threads, on the other hand, are components of a process which can run parallel. There can be multiple threads in the process, and they share the same memory space, as well as the memory space of the parent process. This would mean that the code to be executed, as well as the variables declared in the program, would be shared by all threads in this process. You're probably watching this video in a browser which has multiple tabs open. You might also be listening to music through the Spotify desktop app. So browser and Spotify application are different processes. Each of them can use multiple threading to achieve parallelism. Different tabs in your browser might be run in different threads, and Spotify can play music in one thread, download music from the internet in another, and use a third thread to display the application. This will be called multi-threading. To be honest, modern browsers also use multiprocessing to show you the different tabs. Let's explain the differences between multi-threading and multiprocessing in detail. So, processes have more overhead than threads, as opening and closing processes takes more time. Sharing information between processes is slower than sharing between threads, as processes do not share memory space, as I already mentioned. In Python, they share information by picking data structures like arrays, which requires input-output time. And, which is most important, two processes can be executed simultaneously in the same Python program. On the other way, threads share memory space and efficiently read and write to the same variables, which leads us to the fact that two threads cannot execute code simultaneously in the same Python program. You will ask what is the reason for that, and how will the multi-threading help us achieve parallelization if threads are not executed simultaneously? And I will tackle those questions on the next slide. The Python Global Interpreter lock, or GIL in simple words, is a mutex or lock which allows only one thread to hold the control of the Python interpreter. The GIL prevents race conditions. Race conditions occurs when multiple threads try to change the one variable at the same point of time. In short, this mutex is necessary mainly because Python's memory management is not thread-safe. The impact of the GIL isn't visible to developers who execute single-threaded programs, but it can be a performance bottleneck in CPU-bound and multi-threaded code. As a result, multiple threads happen inside GIL and do not run parallel, while multiprocessing allows you to create programs that can run in parallel by bypassing GIL and use the entirety of your CPU or GPU cores. And you ask, how will the multi-threading help us to speed up our program if the parallelism doesn't occur here? Because it allows us to run threads concurrently. It means that the thread which is idle at the moment, for example, the thread which is waiting for the response of the user or server, will be put on a hold until the other thread is executed. So concurrency and parallelism are related terms, but not the same, and often misconceived as similar terms. So the crucial difference between concurrency and parallelism is that concurrency is about dealing with a lot of things at the same time, and it gives the illusion of simultaneity. On the contrary, parallelism is about doing a lot of things at the same time for increasing the speed. And you can see, for example, the graphic for multi-threading, and you can see that this line is dotted. It means so it does only one thread at the moment, and another thread is waiting. And multiprocessing is actually a solid line, so 3 processes are done here at the same moment of time. And my colleague Vladislav will tell you about the real-life examples of multi-threading and multiprocessing. Thank you.
Hello everyone. I hope so far you should know the difference between multithreading and multiprocessing. However, it is still not clear when to use one or another method. It turns out that multithreading works best when dealing with input-output bound tasks, whereas multiprocessing shines when dealing with CPU-bound tasks, which were introduced at the beginning of the video. Let me give you some examples of input-output bound tasks which can be improved by using threads. For example, a text editing program, such as Microsoft Word. There, one thread could take care of recording the user inputs. Another thread could be responsible for displaying the typed-in text, and the third thread could do the spell checking, and so on. Here, the program has to wait for user interaction, which is the biggest bottleneck. And that's exactly the reason to use threads instead of processes in that kind of a task. Multithreading is also much useful for you as a data scientist. For example, when you scrape the data from multiple web pages, you can simply deploy them in a multiple threads and progress faster. Another relevant example is TensorFlow, which uses a thread pool to transform data in parallel. The CPU-bound tasks are, for example, multiple applications that should run on the same PC simultaneously. That wouldn't be possible without multiprocessing. Other use cases where multiprocessing is often used are tokenization, image augmentation, data filtering, or even complex numerical computations. We would also like to provide you with a small real-world example to solidify the concept. Let us say you're watching Shawshank Redemption on Netflix. Now, two things happen while you're watching Andy Dufresne suffering in jail. One, the application, so Netflix, fetches data from the server. And two, the fetched data is shown to you like a movie on your screen. Thanks to threading, we can divide the two processes into different threads. While one thread fetches data, that is, it is in hang or sleep mode, the other thread can show you the amazing performance of Morgan Freeman. Imagine what would be the situation without threading. You would have to wait for the video to get downloaded once in a while, watch the segment that was fetched, wait for the next segment to get downloaded, and so on. But what if you suddenly got a new mail, or there is a new contribution on Piazza? Naturally, you would like to immediately check it, but you still don't want to pause the video, and that's where multiprocessing comes into play, allowing you to run independent applications simultaneously on the same device. And now it's time to move on to the coding part. We start with a basic example by defining a simple function which we call func. And everything it does, it makes your code sleep for exactly 1 second. Without parallelism, if you run this function 2 times in a row, the first function will start, then sleep for 1 second, until the second function starts and sleeps for another second. With 2 threads, you could improve your code running time by running the second function directly after the first one began to sleep. And if you are sure that both functions do not share any information or do not have any variables in common, you could run those functions simultaneously using 2 different processes. And there is also one useful library we would like to present to you, a so-called Qdm Library, which can track how many threads or processes that have been started are ready at a given moment. You can also see a small example below. So, having said that, we are ready to immerse ourselves into the real code that we prepared for you.
Welcome back, everyone. Now we are on Kaggle and we will present you the code that we've prepared for you. First of all, we will import the time library and define the function func. which we have already explained on the presentation slide. It will just basically sleep for 1 second. And if we run this function 2 times in a row, it will take approximately 2 seconds, exactly 2 seconds to finish. So what we expected, it slept 1 second and then slept another second. But what if we use this threading library and use this function thread, which takes our function func as a target and puts it into a separate thread? And in this way, we define our first thread T1, second thread T2, then we start both of them, join both of them, and ultimately we get what we wanted in just 1 second. So it's 2 times faster than our initial code. And that's because we used not a simple approach when we run 2 functions one after another, but use them as 2 threads. And we also have to join them because otherwise you may get into trouble. For example, here we tried to print the running time of the codes, and basically your threads may be faster than your printing function, and hence you may not get the desired output. We also did the same for processes with multiprocess library, and as you may see, the running time of this code is pretty much the same as of the code with threads. Now let's see at the TQDM or TQDM notebook libraries that we also introduced in the presentation slides. And what we are doing here, we are running a for loop from 0 to 49, and after each instance, we make our code sleep for 5 milliseconds. And when putting this range into the parentheses of as an argument for TQDM function, you may see this nice progress bar. You may also give some specific name to your progress bar. Here it's, for example, the TQDM progress bar, nothing very special. But maybe you don't like this red style and you want somehow prettify your output progress bar, and that's why you may use the TQDM notebook library. And it does pretty much the same, but the output is now this big red progress bar, which just looks nice. And you may also encounter some problem, some error, why your code will not run any further and will terminate. And that's because we just write this display functions that should after 5 instances divide by 0, which is mathematically not defined. And now we come to the essence of this video, and that is the practical use of multi-threading or multiprocessing. You may see here in the multiprocessing folder, we've placed different Excel files. If you're watching this video as a student of DAFA course 2021, you may know all these Excel files because they were part of a case. And there is one certain problem. You should first of all upload all these Excel files to your working directory. And it may take quite a long time. I already uploaded all of them for your convenience, and we will just see the outputs, but you have to believe me that all the code that is provided here is actually working. One important thing that you should check at the beginning of your multiprocessing experience. It's how much cores your machine equipped with. As Matvey explained, it's like an upper bound for your multiprocessing, so how much processes you may run once at a time, and Kaggle is equipped with four different cores, which is quite useful. Here we just printed or put all the files into the files list. And when running the codes, when uploading these files all one after another, like everyone would do it in a simple way, it would take 57 seconds for Kaggle to do so. Or we have also tried it with this progress bar, and it took pretty much the same time. We just put this all this uploading process into a for loop, and basically that was it. But can we improve our code? Can it run faster than 57 seconds? And can we still get our Excel files uploaded to Python? And it turns out it is possible when we, for example, use the pool function of the multiprocess library. As so we have explained, you need some function, and this function just uses a readExcel function of pandas library. It takes some Excel file and uploads it. But what's more important, we use a pool function of multiprocess and use 4 different processes and concurrently upload all the files from the file list, which is all these Excel files on the right side. And after our code was ready, we may see that it took just 34 seconds, which is by about 20 seconds faster than our initial code, which is impressive. And as you may have guessed, we also tried to do exactly the same code with a progress bar, and apparently it works. But so you just have to use one other function from this Qdm library, which the developers of this Qdm library already thought that you may need and use it for tracking multiprocessing, and you do not need to separately define your process pool. You may just write process map and then directly give your function, give your list of inputs, and define here the number of processes. And it works even faster than the previous one, which is impressive. One last thing is that we also tried to run this code with different threads using thread mapping. And it took even longer than the initial code, but our guess is that this uploading process of Excel files to Python is more CPU bound than I/O bound, which is why processes are a better choice in this problem. Also, be aware to put your function into this if name is equal to main statement, because otherwise may have troubles and your code may not be working, especially on Windows. And by having that, we came to the end of our presentation. So we would like to say goodbye and have a nice day.